All right, great. Let's discuss then the traveling salesman problem. That's what we were doing last time. And we did so far one method for solving the traveling salesman problem. Let's just refresh our memory here about what it's all about. The traveling salesman problem is when you have a complete graph, that is a graph which has edges connecting every two vertices, and that graph has weights on the edges, that is numbers. So here's an example. This is called a weighted complete graph. Each of the edges has a little number on it. So in this example, there are 4 vertices. That thing in the middle is not a vertex in this graph. It's just 2 of the edges cross over one another. But there are 4 vertices, and each edge has a label on it. And you think of those edges as representing like distances to go from here to there. You know, this picture doesn't necessarily describe the distances accurately. You could imagine these are 4 different places, and they are at different distances apart. Or maybe those numbers represent the cost to use this or that pathway, something like that. And the traveling salesman problem is to find the Hamilton circuit with minimal total weight. That's called the traveling salesman problem. You have to visit each of the 4 vertices in a circuit with minimum total weight. And last time, I hope you remember this, last time we talked about solving this using what we called the brute force algorithm, or something, the brute force procedure. And that is, you just write down all possible Hamilton circuits. So if these are A, B, C, D, like this, and there's one on the homework for you to do. It's really very routine. I mean, there's not a lot to it. You have to know how to do it, but it's not terribly hard. One way to do this is by brute force. You would list all possible circuits. In this case, there are 6 of them. I don't want to do this whole thing because it's a little taxing, but I would go something like A, B, C, D, A, or I could go A, B, D, C, A, etc. Right? In this example, there would be 6 different ones that start with A. And then you actually add up the weights of those circuits. So the first one here, A, B, C, D, A, I would go A to B is 1. So that would be 1 plus. Next, B to C, that's this diagonal, which is also 1. Next is C to D, which is 3. Next is D to A, like this, which is 4. And that, you add this up, I get 9, right? And then you would do the same thing for all of the other ones, and then you choose the smallest. I don't know if that 9 it really is the smallest. I'm just trying to give you a little reminder of what we did last time. All right, that is called the brute force technique. It is fairly easy to do in the sense that you don't have to think a whole lot to do it, but it will take you forever in a big graph. And that's really the problem with the brute force technique. If you have a really large graph, like say 200 vertices, then really the brute force is not workable in practice, even if you're using a computer. It's too many different choices to check. All right? So this is what I said at the very end last time. Brute force is too intensive to check even using a computer. I mean, for 4 vertices, it's fine. You can do it by hand. But for 400 vertices, you can't do it really, even using a supercomputer. So it's too intensive to check, even using a computer. So in the real world, people who need to solve this problem, which would include people like the example I always use is the delivery truck, which gets 200 packages they have to deliver every day to just like a random bunch of different addresses, and they have to decide which route is the best way to go from all of these addresses one to the next. That is really impossible to find the perfect route. So too intensive to check, even using a computer. I will say, practically speaking, in the real world, like the Amazon trucks, when they actually do this, we don't try to find the best route. Because that's too hard to do. You have to check all the possibilities, and there's just way too many possibilities. Practically speaking, we don't try to find the best route, but one that's pretty good. And actually, there are techniques for finding pretty good routes very quickly that using a computer can do like instantaneously. So that's what I'm going to talk about today. And we have two different procedures for doing this. All right, these are called approximate algorithms. Approximate because they don't actually give you the best possible answer. They give you something that's pretty good, but not necessarily the best. Approximate algorithms for the traveling salesman problem. And there are many that people use in the real world to do this. We today are going to talk about two simple ones. They are called the nearest neighbor algorithm. Nearest neighbor, which I will write as NN. And the second one is called the sorted edges procedure. All right, so those are the two methods that we're going to talk about. So in total, you know, when it comes to the final exam, really there are three that we are going to talk about. The brute force, which we did last time, which you can do by hand on small graphs, but on big graphs is more or less totally impossible. And then the nearest neighbor and the sorted edges. These ones actually you can do them even on quite big graphs, and they're fairly easy to do even on big graphs. All right, let's start off with the nearest neighbor. Nearest neighbor. And maybe I'll just use the same example if you don't mind. I know it's harder for you to do this than me if you're writing this on paper. But I'm flexing it. All right, let's do that same graph again, and I want to describe how the nearest neighbor algorithm works. All right, it's much easier than doing the brute force, although you have to actually think a little bit. So the thinking, I suppose, is a little bit harder, but you can do it a lot faster than the brute force. So what you do is, first of all, choose your starting point first. Choose a starting point. Now, when you're doing this on a homework or on a test, I will often just tell you where to start, so that's fine. There's no trick for choosing the best starting point or whatever. You have to decide kind of arbitrarily some starting point. So let's, let me just describe the method and then we'll do this particular example. Choose a starting point and then pick edges one at a time. I will say pick edges as you go. And each time, use the cheapest edge. And the cheapest edge is, if you think of those numbers as representing distances, this is called the nearest neighbor. That's why the name of this thing is called the nearest neighbor procedure. All right? You choose a starting point, and then you just choose edges as you go through the graph. And each time you choose the cheapest edge which is available at your whatever point you are at. And you have to make sure as you're doing this that you don't revisit. That says revisit. Don't revisit any vertex. You know, we're looking for a Hamilton circuit which is not allowed to revisit any vertex. Until the end, of course. It is a circuit, so you should end up back where you started at the very end. But before that, don't revisit any vertex that you already revisited. Don't revisit any vertex until the end, where you end up where you started. All right? It's easy to do. Let's just try this particular example here, and let's just say I'm going to start starting at A. See how it goes if we do that one starting at A. So I'm going to write it A first, all right? And you look here, starting at A, and you ask yourself, what is the cheapest edge available to me from this point? I got the 1, the 4, or the 5. The answer is the 1, all right? So from here, the cheapest edge to choose in terms of the weights is the 1. So I'm going to begin by starting at A, and I go A to B, right? And maybe if you have another color, you could just scribble in on the picture. That's the first edge that I chose because it was the 1 versus my other 2 options were 4 and 5. So from there, I am going to use the cheapest edge available, also called the nearest neighbor. If those numbers represent distances, then B is only 1 distance away rather than D, which is 4. Okay? And then you just continue from there. So from B now, I got 2 choices. I could take the 1 or the 2. And which one do you pick? You pick the 1. All right? So I go A to B, and then I go B to C, because from here, maybe I'll just put parenthetically here, that's a 1. B to C is also a 1, right? So I choose this one now. And so on, right? This is not, I hope that you can see what I'm doing here. It's not rocket science. All right, what about next? So now I'm here, I'm at C. My choices are 5 or 3. Now actually, you can't even choose this 5. I mean, the 5 would be a bad choice anyway, but remember, you're not allowed to go back to a vertex that you already visited unless you're actually done. So I am going to choose the 3 next. So that's C to D is a 3. C to D, which is 3. All right. And then from D, actually, you have to just go back to A from D. All right. It's a 4. My 2 choices are the 2 here or the 4. But if I did the 2, that would make a subcircuit, which is not allowed. So you got to go back across D to A, which is 4. All right. And that's my answer. This is what you get doing the nearest neighbor starting at A. All right. So my answer is the way you would write this if you wanted to write, on a homework or something, using the nearest neighbor starting at A. The circuit that I get is A, B, C, D, A. That's a little obvious. I just wrote this stuff again, but as a circuit. A to B, then B to C, then C to D, then D to A. All right. And if you like, what's the total weight there? The total weight, you would add up those numbers, right? 1 plus 1 plus 3 plus 4, which is 9. That's the same one I said before with the brute force. All right. This is the nearest neighbor method. It's fairly simple in my opinion, and this is the kind of thing that anybody would come up with if you found yourself in the real world having to do this. This is not a bad way to go about doing things. All right. You have to make a bunch of choices one after another. You just choose the best option every time. That's called the nearest neighbor procedure. Any questions about that? It's pretty simple, I think. Let's try. One thing I want to say. The nearest neighbor, I hope you will agree with me, the nearest neighbor is much faster than the brute force. In the brute force, you have to write down all possibilities, which requires, brute force requires something like n minus 1 factorial steps. You have to write down all possible rearrangements of the letters, all possible Hamilton circuits, which is a lot. It's a factorial, which is very, very big for large graphs. But the nearest neighbor requires, where n, of course, means the number of vertices. Here there were 4 vertices. How many steps did it take me to do this? I would say it's basically 4 steps. You just kind of do one at a time, and that's it. So with n vertices, the nearest neighbor requires really like n steps. This is much less. Much, much less, right? The factorial is super big when the n is large, but when the n is large, the nearest neighbor really doesn't require many steps at all, all right? If you had a truck full of 200 packages, doing the nearest neighbor would take you 200 steps, which on a computer will happen instantaneously. Versus 200 factorial will take millions of years for the computer to finish. All right. Another thing to notice. This is the important thing about the nearest neighbor. It's much faster than the brute force method. All right. That's why it's useful. Another thing to notice is, unfortunately, it doesn't always choose the best route. Unfortunately, the nearest neighbor doesn't always choose the best route. For example, here's another example where actually in this case the nearest neighbor doesn't choose the best route. So same thing, I have to give you the weights here. I'm going to go 2 on the top, 10 over here, 4 here, 5 here, 1 and 3. All right. And if we do nearest neighbor here, starting at A, can anyone say what would you go? So from A, where would you go next? You start here. You choose your best option from there. What do you say? To B, I think. Yeah, the 2 is the best option there. So, I mean, this really, once you know what you're doing, you can more or less do this all in your head, right? I go from A to B is 2. Okay, then from B, where should I go? To D. Yeah, that's a 1. So I go A to B to D. If you like, as I go, I can fill these in, right? I use those. Now from D, I can't go back to A because that's well, it's a 4, which is worse than 3. Also, that would make a that would finish too early. That's a subcircuit. So I go back to C here, and then from C, my only option is to go back to A along this edge, which is 10, and that actually is not a very good. So this, if I were to add the weights here, this is 2 plus 1 plus 3 plus 10, which is 16, all right? But actually, you can do better than that. So this is what you get if you do the nearest neighbor starting at A. You're going to end up just going around the outside. Unfortunately, though, you made sort of what seemed to be the best choice in each step, but it forced you into doing this 10 at the end, which is really quite bad. So, there are better ways, can I just say, but something like, I believe if you go across the middle, A, D, C, B, A is better. So that would be this way, A, D, C, B, A, like that. And if I add these numbers up, it's 4 plus 3 plus 5 plus 2, which is 14. All right, so the moral of the story is the nearest neighbor method does not always give you the best result, all right? Sometimes if you make the best choice every time, that's still not the best route overall, right? So, so in this example, the nearest neighbor did not choose the best route. Sometimes it happens, all right? If you want the best route every time, you have to use the brute force, which is impractical in the real world. But you know, something's got to give. So if you don't want to use the brute force, then your method might be giving you bad results sometimes. All right. And I got one last sort of oddity about the nearest neighbor, and then we'll talk about the other one, the sorted edges. Actually, I had an example for you to try, but one last nearest neighbor oddity. It matters where you start. Typically on a homework question or something, I would just tell you where to start. But if I leave it up to you, you can choose whatever, but actually those different choices may affect the result that you get at the end. So, for example, actually this is the same as my first example. If my weights go 1 here, 5 here, 4 here, 1 here, 2 and 3, like that. If we start at A, it's going to be A, B, C, D, A. This is the one we already did. This is the same graph from before. And if we start at A, we should choose the 1, and then the 1, and then the 3, and then the 4 back up. All right, so this one is 9. But what if I start at B? Will I end up choosing the same circuit? So starting at A, I'm going to make 4 copies of this. Well, I don't want to have to redraw all the numbers every time, but this one, A, B, C, D, A, is this, right? A, B, it's that. All right, so that's what we get when we start at A. What about when we start at B? From B, what should you choose? Actually, this is slightly ambiguous. You could either go across to A or you could go down to C. There's a tie, all right? When there's a tie, if you're doing the nearest neighbor, you basically choose at random. If I was giving you this question on a test, I would probably make it so that there are no ties, just so that everybody's going to end up with the same answer. But let's say from B, I'm going to go across the C first. So I'll go B, then C. From there, what should I choose? So here, if I were drawing the picture, I chose that edge already, and I'm right here now. What do you say? I go across the bottom to D. That's a 3 versus a 5 here. I don't want to choose the 5. I want to choose the 3. So I go across the bottom. That's a D. From there, I cannot go up because that makes a subcircuit. So I have to go across the diagonal here again, which is to A. And then across the top to B again. So this is that. Actually, that's the same as this, isn't it? I mean, it's the same pathway. Whether you decided to begin at A and end up at A or begin at B and end up at B. This is the same. This is also a 9 if you were to add up the answers. So that's the same. All right. I said it matters where you start. In this, so far, that didn't matter. It's the same either way. What if I start at C? I'm going to try to make this, I may have to scroll. That's all right. What if I start at C this time? Starting at C, where should I go next? What do you say? D, yeah. My choices, not D, B, right? My choices are the 5, the 1, or the 3. So I'm going to take the 1. So I go up this way. It'll be C to B. Then from B, what are my choices? I could go down for 2 or across for 1. I should take the 1. So I go across the top here. C, B, A. From here now, I must go down the diagonal because I can't make a subcircuit, and then across the bottom. So actually, again, I got the same thing. This is C, B, A, D, C, right? Which again is a total weight of 9. It's the same, again, that same sort of X-like pattern, all right? Or my final option would be starting at D. What do we get in that case? All right, starting at D here, which way should I go? I should go to B. That's 2 versus 4 or 3. I pick the 2. So starting at D, I'll draw that one over here. And you can see this one's going to be different because I'm using that edge on the right, which I didn't use in any of the other ones. All right, so it's going to be D to B. From there, I can either go across the top or down the diagonal. And actually, that is a little ambiguous, either because they're both 1s. Let's just let's choose the diagonal, I suppose. D to B to C. That's this diagonal. Or you could have gone across the top, and actually you'll get different answers either way. And then to finish from here, it has to go up and down the diagonal to avoid finishing early. So it's like this. All right. So it's D, B, C, A, D. And the weight of that, if you add those numbers up, is D to B is 2, then this 1, then 5, then 4. So 2 plus 1 plus 5 plus 4, which is 12, I believe. All right. So that is worse than the other 3. All right. The moral of the story is when you change the starting point, you may actually get a different answer. It matters where you start. All right. Actually, in this particular graph, I went through all the possibilities. This 12 is actually the worst possible way to do it in this particular graph. Sometimes the nearest neighbor will give you bad answers. That's just the price you pay for not doing the brute force. All right? Any thoughts about that? So there is a fancy, very slightly fancy, because of this, so different starting points give different answers, right? That's what I said. Different starting points may give different answers. All right, and because of this, we can, if you really want the best answer, but you really don't want to do the brute force, we can do something called the repeated nearest neighbor. What that means is you just try every different starting point and do it, like I just did. Do it 4 times and choose the best out of all 4. This is still a lot faster than doing the brute force, and it gets you a pretty good answer. It's still not guaranteed to be the best answer. The repeated nearest neighbor, that means you do nearest neighbor repeatedly, starting from all possible vertices. And then when you're all done, you choose the best overall. Now there may be many ties or whatever, but this is the idea between the repeated nearest neighbor. So when we're done, choose the best overall. This will hopefully avoid you getting a bad answer just because of where you started, right? If there's a better starting point, you will find the better starting point. That's called the repeated nearest neighbor algorithm. All right? I got one for you all to try. I didn't even do an example of this. I think it's straightforward enough. I will let you all see what you can do with this. So this is with 5 vertices, and rather than make you copy it down from the screen, I printed this out for you. So what I want to do is I would like you to, I put the same graph on both sides of this paper here. Your job shall be to find the best Hamilton circuit you can using the repeated nearest neighbor. So that means do it first starting at A, and then do it again starting at B and C and D and E. I don't know if this sounds tedious to you. Actually, each one of these is fairly easy to do. And then, using those results, choose the best answer overall. All right, can we talk about this one? This is slightly tedious, I suppose. You have to add all these numbers together. Sorry, this is kind of hard to see on the screen. I hope you can see it all right. Yeah, it's all right. So, when I start at A, what's it going to do? So we start here. A, I could choose the 7, the 1, the 3, or the 5. I'd go with the 1. That's the nearest neighbor from the first part. So that's A to D, like this, which is A to D. That's a 1. Then from the D, I could go the 4. This is 2 or 5. I'm going to take the 2. That's this one. So I go A to D to B, which is 2. Then from the B, I go, I believe the 1 is the cheapest option at this point. So from the B, I take the 1 here, which goes to C. That's a 1. And then now from the C, my choices are 3, 4, or 5. Actually, I cannot do the 3 because this will revisit my starting point too soon. I cannot do the D because I've already been to D before, so I have to go back to E this way. That's the 4. And then finally from E back to A, and that completes the circuit. All right, E to A, that's 7, and if you add these numbers up, you get 15. I hope that's what you got for, if I start at A, it's 15. All right, what if we start at B? I suppose it would have been nice if I gave you even more copies of this picture, but starting at B now, it's not so hard to redraw just this much, right? I'm going to start at B, which is over here. And where should we go starting from B? Where did you go next? Somebody shouted out. To C, that's a 1. Is that her as she was leaving the room? It's like walking away from an explosion without flinching, just like that. That's a baller move, as they say. From there, C goes up. I believe you should take the 3 next. Your choices are the 3, the 4, or the 5. I take the 3 up to A. So this is B, then C, then A. That was a 3. From A, my choices are 1 or 7. I take the 1 down to D. And then from there, I believe you have to go to E and then across back to B. So that would be 4. And back to B is 3. So these, when you add, you get 4, 5, 9, 12. Am I right? Anybody agree? Yeah, great. And so on. Could we, just for the sake, I don't know if we need to sit here and watch me do all of these, just for the sake of completion. Can somebody shout out, what did you get when you did this starting at C? Anybody get this far? I know some of you did.
C, B, A, E, C.
Say it again.
E,
E, C. All right. Anybody else agree? Yes. Okay, they agree. And what do the numbers make here?
1, then 2.
Can you just give me the total?
I didn't do it.
Oh, anybody else do this one? 15. Okay. I just want to get these down just in case, people, I know some people finished, some people didn't. So if you didn't finish, you can work these out later on. What'd you get for starting at D? Somebody who did this one? What do you say?
B to A to C to B to E to D.
Okay. For
Total 12.
12. Anybody agree with that? Yes? Okay, and then E? Who did it starting at E? Yeah, can you say?
I got E, B, C, A, D, E, and I got 12.
All right. Anybody else agree with that? Excellent. All right. So, hopefully you got these. If I stopped before you were done, I hope you got some of these at least. All right. One little thing. What if I asked you, using the repeated nearest neighbor, what's the best route? Well, the best you can do among these that are presented before us is 12, right? What about, I could ask the question in this way. Use repeated nearest neighbor to find a good circuit starting at A. What if I said this? Now this is a little weird. This is a question that I always put on the homework and people get confused about this because I said use the repeated nearest neighbor. That means you go through and do this for all the different starting points. And then I said find a good circuit starting at A. Using the repeated nearest neighbor means you have to do all of these. What this means when I say it this way, find a good circuit starting at A, it means write your answer starting and ending at A. So when I look at this, you do it, first of all, with all the different possible starting points, A, B, C, D, and E. And then, from all of those, you choose the best one. Now, I have some ties here with 12. There are actually 3 of those, which gave me 12. But let's say I choose this as my best one. So I'm going to say, you do the repeated nearest neighbor. I got crazy colors here. I didn't switch back to black, sorry. Do the repeated nearest neighbor. And then write your best circuit as if it started at A. All right, that's my strategy. So in this case, sorry, I scrolled out a little bit. In this case, my best one was the 12. Now there are 3 different 12s you kind of chose from, but let's just choose the first one there. B, C, A, D, E, B. And that's this little picture here. And what I said is, I'm going to use this circuit, but write it as if it started at A. So rather than starting this at B and going through to this B, I start at A. This is, I'll just write it as it was before, B, C, A, D, E, B, right? How can I write this same circuit, but starting at A? It would look like A, D, E, B, C, A. What I did was I just took that and that, right? This, as written, has A in the middle, but you can write the same path just starting with A at the beginning and then do the same thing. So I started with A and then I did D, E, B, and what comes after the B is C, and then back to A. That's what this comes from. So this is A, D, E, B, followed by B, C, A. All right? Given any one of these circuits, you can rewrite it starting from some other point. All right? Here it's written as if I started at B and ended up at B, but I can write the same thing as if I started at A and ended up at A. All right? So you may be called upon to write your answer starting at a particular point. It doesn't mean that's the one that you got when you started at A. It means this is the best one that you saw overall, and you write it as if it were starting at A. All right? Yes? It's because this circuit, remember what that represents is this. B to C, it's this, right? That's what the first circuit was. Is that right? Yeah, if you write those letters, it gives you this path. Now you can write that path as if it started at B and ended at B, but I could write this same path as if it started at A and ended at A. And that's what it is. It's the same path. It's just deciding where to write the starting point. You could write it starting wherever you like. All right. Excellent. This is all I wanted to say about the nearest neighbor procedure. Any leftover questions? Like I said, you will see questions on our final optional homework assignment. All right, great. The very last thing that I want to say, and we can do this in our remaining 30 minutes, is the sorted edges algorithm. That was the other one that I said I wanted to talk about today. And actually, I thought this might be fun. I have another handout. This is going to be like a little fill in the worksheet kind of thing. I don't know if people like doing that. But you can, like all of your notes about this, should fit on this little paper here. If you don't mind not having it in your regular. All right, this is the sorted edges algorithm. Let me get mine here. All right. This is the same example there, but we're going to do it in a different way. This is the sorted edges algorithm. All right, I'm going to tell you how to do it, and then we'll do this example, and then on the back is another example for you all to try, and that'll do us, I think. So this is the sorted edges algorithm. It's another way of finding a pretty good circuit. It is also not guaranteed to give you the best one, but it'll give you a pretty good one. All right, the sorted edges algorithm. Here's how we do it. You start by writing out the edges. Write out the edges in order by weight. This is why it's called the sorted edges algorithm. I'm going to write out the edges, that is just like the weights, in order. What do I see when I look at the picture? I see a 1. I see another 1. Maybe as I go, I'll kind of circle them. There's a 1. There's another 1. I see a 2 here. I see 2 3s here and here. All right. I hope everyone sees what I'm doing here. I'm just writing down all the weights that are available one by one. I see 2 4s. I see a 5, 2 5s, and a 7, and that'll do it. All right. So that's step 1. Write out all the edges in order by weight. That's why this is called the sorted edges procedure, because I have just sorted the edges in order by weight. And then you build your circuit by choosing these edges, starting with the cheapest ones and going to the end. So it's like the nearest neighbor, but you don't actually care about a starting point. There's no starting point. You just choose these edges one by one. So I'm going to say choose these edges one by one. I'm going to say don't try to connect them up. So you don't choose them based on I choose this edge and then from there I choose this next edge and then from there I continue to this edge. It's not like that. You just choose a bunch of random edges in isolation. Don't try to connect them up. They will naturally connect up if you're doing it right. So you don't have to try to make one connect to the next one. You choose these edges one by one. Don't try to connect them up. And you just have to make sure as you choose them, you don't do anything illegal. And what counts as illegal is never make a subcircuit and never make a three-way junction, because that's not allowed in a Hamilton circuit. All right? This is the sorted edges algorithm. You choose these edges in order. The idea is, for example, I have 2 1s on the picture. I want to make sure I use both of those 1s. That's what the sorted edges is all about. Rather than just going from one point to the next, making the best choice each time individually, I am going to look overall at this whole thing and say, I want to choose this one. I also want to choose this one. Even if they're not joined up together, it doesn't matter. So let's try it. In this particular example, you look through your list of edges and you just start with the cheapest ones and you choose them in order. So I'm going to choose the 1. Now there's 2 1s on the picture. Which one is it? It doesn't really matter because I choose that one and then I immediately also choose that one. All right? So I choose this one, I choose this one. Next, I choose the next best, which is a 2. So you should ask yourself, is the 2 actually legal here? This is the 2. If I choose the 2, does that make a subcircuit or a three-way intersection? No, it does not. That means the 2 is legal at this point. So I also choose the 2. I just chose the 2. All right? Next, I should pick the 3s. You will notice these edges that I picked so far, they do join up together, but that is, I wasn't trying to make them join up. They naturally do join up if you're doing it correctly, but you don't try to force it. For instance, I picked the 2 1s, even though they were not next to each other. It's fine. What about the 3s? So there are 2 3s that I want to choose, although I think actually one of them is illegal at this point. This is one of the 3s, this diagonal, or this 3 straight across. Which one can I use and which one can I not use? Remember what you cannot do. You can never make a subcircuit. You also can never make a three-way junction. Yeah. You can't use the diagonal one? I think actually I can use the diagonal one. Maybe you're concerned that this makes a subcircuit, like right here. Is that what you're thinking? That actually doesn't count as a subcircuit because this is not a vertex here, right? That doesn't actually make a circuit of vertices. It's just on this picture the lines are crossing, but that's okay actually. It's okay to cross the lines over. It is not okay to, actually this one, oh, that does make a subcircuit. You're talking about this circuit. Yes, she's right. I'm sorry for doubting you. I should have had more faith. Yeah, that's a subcircuit. Illegal. So this 3 is not allowed. I'm going to X this out, right? Because that makes a subcircuit. It makes those 4 vertices would make a circuit by themselves, and that is not allowed. What about the other 3? I said one was bogus and one was okay. Actually, they're both not allowed. Why is this 3 not allowed? Yeah, that makes a 3-way intersection over here. Also not allowed. So I will X that out. I'm using a different color X just so you can tell. This makes a 3-way intersection, and that's not allowed. All right, so both of the 3s are out at this point. My next best would be, I suppose, to use the 4s. I have a 4 over here. Actually, that's not allowed because that would make a 3-way intersection at the bottom there. So this 4 is out. I'm not going to use the 4. What about the other 4? Is this one okay? I think actually this one is okay. So I pick that 4 also. Jerk. And now actually, if you look here, there's only one more edge that you can do to finish it off. It would be the 7, all right? Although you could look individually through the other ones. This 5 is no good because it would make 3-way intersections on both ends. Also, this 5 would make a 3-way here. So I got to do the 7. Anyway, I cross out the 2 5s, and I finally pick the 7 right there. And so what is my answer? Well, my answer is that circuit. When I write it down, I will just say, write your answer. Starting wherever you like. So usually in a question like this, I would say, use the sorted edges to give me an answer which starts and ends at B or something like that. I will tell you where to start. So if I said, starting at B, then you look at the picture that you've got and you read those edges as if you were starting and ending at B, which is over here. And actually, even so, you have kind of 2 ways to do it. I could go around this way, or I could go around that way, and you can do it either way you like. So I will go B and then to C, and then from C it goes to E, and then to A, and then to D, and then to B again. All right? So if I told you to write your answer starting at B, this is what you would say. Although I could have also told you to write your answer starting at A, and you would say something similar to that, but starting at A. All right? This is the sorted edges procedure. Let's just do one more together, and then there's one on the back for you all to try. So this one here, different numbers. Picture looks similar. I think it's different numbers, isn't it? Yeah, it's different numbers. All right, so again, I begin by making a list of the edges. Now, if you are used to doing this already, you might decide that you can maintain this list of edges in your head. And that's okay with me if you like. Rather than writing them down in a list like that, you can just look at the picture overall and ask yourself, what's my best options? The best ones to begin with are the 2 1s. But I believe we have just 2 of each number here. 2 1s, 2 2s, 2 3s, 2 4s, 2 5s. All right? And again, you choose edges just sort of from left to right, starting from the cheapest ones over to the more expensive ones if you have to. I'm going to try to choose the 2 1s to begin with. And actually, I think there are 2 1s and I can use them both, right? I have this one here and also this one across like that, okay? Again, you do not try to connect them up one to the next choice. No, you just choose whatever you want as long as you don't make a subcircuit or make a 3-way intersection at a vertex. So I choose this one, I choose this one. What about the 2s now? I have this 2. Am I allowed to use that 2? They're saying no. I think the answer is yes. I am allowed to use this 2. I don't know, are you worried that it makes a circuit here? That doesn't count as an actual circuit because that's not a vertex, right? That's just on the picture the lines are crossing, but that's not relevant. I can use this 2 right here. So I picked that 2. The lines are crossing, but it's not a subcircuit because they're not crossing at a vertex, all right? What about the other 2? This one over here, is that legal to use? I see some nodding heads. Yeah, this 2 is also legal at this point, so choose this 2 also. All right, what about the 3s? I gotta consider the 3s. This 3 here, not allowed because it makes 3-way intersections on both sides. What about this 3 here? Also not allowed. It makes a 3-way intersection at B. So those 3s are both not allowed. What about the 4s? I have a 4 here. which makes a three-way intersection at B, so I can't use that. I have another 4 here, which makes a three-way intersection at E, so I can't use that. So the 4s also are out. And then the 5s. I have a 5 here, which makes a three-way at the top, or a 5 here, which actually is legal, like so. All right? And that's my answer. It's kind of a fishy type thing, rotated, I guess. Fishy swimming down. They do that sometimes, don't they? All right, so what's my answer? Now, I said, check it out. If you read the fine print, I said, find a good Hamilton circuit starting and ending at A. So I told you where I want you to start. That has nothing to do with the procedure as done. It's just about how you write the answer. So when I write the answer, I start it at A, and then from A, I could either go down to C or to B. Let's just say I go B next. That's just a choice of how you're going to write this. And now I do this pattern, A to B, then E, D, C, A. So this is A, B, E, D, C, A. There you go. Starting and ending at A.
But you could also write it like A, C, D, E, B, A.
Yes, you could go sort of around the circle the other way. That would be A, C, D, E, B, A, which is the reverse of what I had written.
Right?
Yeah, either answer is acceptable. I suppose if I really wanted, I could say, give me the one that starts at A and then goes to B, and then there's only one way to do it. All right. In our remaining 15 minutes, can you try the one on the back? It's a big one. You can handle it. This big one would be totally unreasonable to do with the brute force. It would take you forever. But with the nearest neighbor or the sorted edges, not a big deal. So your job here, I hope you can remember the other one too. Find a good Hamilton circuit starting at A using nearest neighbor, first of all, which I think is a little easier. And then do it also using the sorted edges. See if you might get the same answer, you might not.
just redo this entirely. Yeah. Thank you.
Doing okay?
Okay.
Is this the sort of edges?
All right. Okay. All right, can we go through these just so that we don't run out of time entirely? So I was going to do the nearest neighbor first because that's what I said first. And I said Hamilton circuit starting at A using the nearest neighbor. I didn't say the repeated nearest neighbor, which is the one where you have to do it from every different starting point. Just nearest neighbor starting at A. You start at A. I find rather than drawing on the picture itself, I like to make a little sort of side diagram. A to E for 8, then E to F. Where did you go next from here? I already used the 11. I can't use the 9 because that would make a subcircuit here. I think it should be the 7 up to C. Anybody agree with me? Yes. So next I went up here for 7. That's to C. And then from the C, my options are to D or B. All the other ones have already been visited. And it should be the B because that's a 1 versus a 13. So I go across to B next. And then it has to, in order to finish this as a circuit, it has to go D and then back to A to the beginning. All right, so this is the circuit that I got. C to B to D to A. Anybody agree with me? I think so. And what, just for the sake of saying it, what are the numbers when you added these up? 56? Anybody agree?
I have 57.
57. Oh, okay. Anybody agree now? 57? All right. They're saying 57. If 2 people say 57, I agree with them. Okay? So that's what I got with the nearest neighbor starting at A. What about the sorted edges? So this one is, you got to write down the numbers first. So I'll go 1, I believe 7, 8, 9. Please shout out if I miss one. It's easy to miss one while you're doing this. There's a 10. There's a 11. There's a 12. There's two 13s. There's two 14s. There's three 15s. And a 20. Did I get them all? I hope so. All right. So, again, I will make myself sort of a little miniature version of this picture that I can scribble on, just so that I don't deface the original. I should start by choosing the 1, which is the one going across the top. So I picked the 1 first. Next choice would be the 7. I like the 7. Right? The 7 is no violation. Actually, when you're doing the sorted edges, the first 2 will automatically never have any conflict. You're always going to take the first 2. The 8. The 8 goes here, and I believe that does not make any kind of three-way or sub-circuit, so I picked the 8 also. The next is the 9, which is here. Is that allowed, given what I've chosen already? I think the 9 is allowed. That will be this one right there. And that does not make a three-way or a sub-circuit. Okay. I'm feeling good so far. Next is the 10. Can I choose the 10? That would be here. No. The 10 would make a three-way intersection right there. So I do not use the 10. How about the 11? Actually, rather than going through all these numbers, I think you can, just by looking at what we've got so far, you can tell what are the only 2 edges to fill in to finish this off. I have to somehow connect this to that going through this edge, or this vertex, right? It has to go here and then here. That's the only way this is going to work. Any other way of finishing it would make three-way intersections or subcircuits. All right? I hope this is the circuit that you got when you did the sorted edges procedure. Now, to write my answer, I said, write your Hamilton circuit should be written starting at A. So I'm going to write this as if we started at A. It should be A, and then let's go down to F first. Or if you prefer, you could go to E, but I'm going to do it this way. A to F, and then up the diagonal to C. I'm just reading my picture that I've got here. Then across to B, then down across to D, E, back to A. A, F, C, B, D, E, A. This is different. Did anybody add up those numbers? I don't know if you even got the same answer as I did. Nobody. Can I add them up? This is 1, 7. No, it's not. A to F is 9. F to C is 7. C to B is 1. B to D is 15. D to E is 14. And E to A is 8. When I add these up, I get 10 here, 17, 32, 46, and 8, 54. I don't know if that's right. It'd be a tragedy for this semester to end with the wrong number, but you know how much I care about right numbers is not very much. All right? I hope I did it right in any case. That's what I care about.